Hello all, welcome to Advanced Engineering Physics, Part 6, Magnetic and Dielectric Materials. This is Dr. S. Deepthi, Assistant Professor in Physics, Department of H&S, MLR Institute of Technology. So today we are going to learn about the types of polarization. In previous video lecture, we have already seen about the types of polarization. Electronic polarization, orientation polarization, space charge polarization and ionic polarization. Now, in this video lecture, we are going to have the mathematical formulation of these, and also we are going to have how the orientation polarization and how the space charge polarization occurs for different types of materials. Okay. So, now electronic polarization. What is electronic polarization? Simply see here. An electrical strain is produced in an atom due to the application of electric field. It is called as electronic polarization. So, strain occurs in an atom. Okay. So, it is the result of displacement of positively charged nucleus and electrons of atoms in opposite direction to the applied field. Yes, yesterday in the previous video lecture, what we have learned? We have learned about polarization means separation of positive charge and negative charge. Here we are going to apply the polarization mathematical equations for the polarization of positive and negative charge. Consider an atom now. Now the atom consists of what does the atom consist of? Atom consists of a nucleus and surrounded by the electrons revolve in a particular orbitals. Now here what we are going to see here, we are going to show that nucleus is situated in one place and all the negative charge electron cloud is situated at another place within the atom itself. Then they are separated by a small distance and these have displacement will be occurred between them. Due to the displacement, we are going to have the electronic polarization. Okay. Understood? The extent of displacement of charges is proportional to the strength of electric field. Therefore, the dipole created within each atom and the dipole moment is proportional to the electric field. So, the dipole moment is equals to this is electronic polarization, we call as EL, is proportional to E, and that is equals to mu E or mu EL is equals to alpha E into E. Okay. So, sometimes they will write as mu EL and sometimes they will write as mu E. No issues. So, mu E, the polarization is directly proportional to the applied field and that mu E is equals to alpha E into E. Okay. This electron polarizability increases with increasing the volume of atoms and dielectric constant and is independent of temperature. Monoatomic gases exhibits only this type of polarization. So, the example for electronic polarization comes from the monoatomic gases. Now, the derivation. See the diagrams over here. So, the diagrams clearly says that a nucleus exists with a positive charge Ze and also with a radius r. The first figure. Okay. Now, Ze is the positive charge and minus Ze is the negative charge, and there is a x is the distance between the positive and negative charges. So, okay. So, the original position, if you see the original position of nucleus and the electron cloud, these are the original, this is the nucleus and this is electron cloud, right? So, this is the original positions, they are separated by distance x. Now, when they are displaced from their original positions, what happens here? Okay, let us see what happens here. They are displaced, the original position is displaced much with the application of the electric field. Okay. Now, when the nucleus and the electron cloud are shifted from their equilibrium positions, an attractive Coulomb force is created. So, there are two types of forces will be created here. One is attractive Coulomb force. Another one is, we can say opposite force will be created. Okay. So, this force will be created and it will tend to separate the nucleus and electron cloud of the atom shifted from the equilibrium positions. So, their equilibrium positions will be shifted due to the Coulomb's force. Okay, so the Coulomb's charge density, due to that, the opposite forces, new equilibrium position is created, and the charge density rho is equals to Ze by 4 by 3 4 third pi r cube, where r is the radius of the total where r is the radius, okay, and Ze is the charge. So this is the charge density my Ze by 4 third pi r cube, right? Volume of the means charge density means what? Charge per unit volume. So the charge is taken as minus Ze, and 4 third pi r cube is the volume of the sphere, right, of radius r. Now come to the negative charge on the sphere of the radius x. So we have sphere of radius x that is created between positive and negative charges, that is equals to 4 by 3 pi x cube rho. Okay, 4 third pi x cube rho. Now substitute rho here, minus Ze 4 by 3 pi x cube by 4 by 3 pi r cube. Okay, so in the place of rho, what we are doing? Minus Ze by, we are substituting minus Ze by 4 by 3 pi r cube. So this is the step substituted over here, and that will become minus Ze x cube by r cube. Okay, so the Coulomb force of attraction between the nucleus of charge Ze and the electron cloud at a distance x from the nucleus is given by. So the Coulomb force of attraction is equals to Fc is equals to Ze into this negative charge of a sphere is there, no, by 4 by 3 pi x by 4 pi epsilon at x square. Okay, so this is the Coulomb force. The Coulomb force is equals to Fc is equals to Ze into the charge, negative charge of the sphere x, Ze into negative charge divided by 4 pi epsilon x square. This is the Coulomb force. Now substitute over here, minus Ze into Ze x cube by r cube. I have written minus over there, 4 pi epsilon x square, that will become Z square E square x by 4 pi epsilon naught r cube. So okay, so here epsilon is the permittivity of the space, and epsilon naught is the epsilon is the permittivity of the material medium, and epsilon naught is the permittivity of the space. So in general consideration, we are going to consider as epsilon naught itself. Okay, so we have obtained the Coulomb force as Z square E square x by 4 pi epsilon naught x cube, 4 pi epsilon naught r cube. Okay, so this is the final Coulomb force of attraction. Now this force will be balanced by Lorentz force. Okay, so Coulomb force, what it will do? It will be it is going to attract the nucleus and electron cloud, whereas the Lorentz force acts opposite. There is a Lorentz force, Fl is equals to Ze into E. It is the Lorentz force is directly proportional to the applied electric field. So under equilibrium conditions, the Coulomb force of attraction will be equal to the Lorentz force. So the Coulomb force of attraction Z square E square x by 4 pi epsilon r cube is equals to Ze into E. So we are going to have E is equals to Ze x by 4 pi epsilon naught r cube. So this is the electric field. Okay, right? Due to the shifting in the electron cloud, an induced dipole moment will be produced. The induced dipole moment is equals to mu E is equals to Zx. Okay, so and also mu E is equals to electron polarizability is equals to mu E is equals to alpha E into E. So we are going to equate mu E is equals to ZE into X is equals to alpha E into E. So E is equals to ZEX by alpha E. This is another E. Now we are going to equate this equation 1 and this equation 2. So that is equals to ZEX by alpha E is equals to ZEX by 4 pi epsilon naught R cube. So by consideration of the equation, we are going to have alpha E is equals to 4 pi epsilon naught R cube. This is the electron polarizability. Okay. So what we are going to do? First, in this electron polarizability, there will be a shift in the position of the nucleus and also electron cloud. Due to the shift in the position of the nucleus and electron cloud, a Coulomb force of attraction will be developed in between them. So the Coulomb force of the attraction is given by some equations. Then afterwards, what we have solved by taking the Lorentz force. The Lorentz force and Coulomb force are opposite forces, and under equilibrium conditions, these two forces will be maintained in order to maintain the atomic stability for that particular atom. So the atomic stability is maintained by the two forces. Under equilibrium conditions, these two forces are equal, and then we are going to equate the two Coulomb force of attraction and Lorentz forces. We are going to equate them, and we have obtained the electric E equation. Okay, the electric field in equation is obtained over here, and also we have obtained electric field equation by another thing, like from the induced dipole moment. The induced dipole moment is equals to mu E is equals to ZE into X, and also the electronic polarizability is given by mu E is equals to alpha E into E. Okay, so we have equated them, and finally we got alpha E is equals to 4 pi epsilon R cube. Okay, so this is the final equation of electronic polarizability, 4 pi epsilon naught R cube. Okay, so this is electronic polarizability. Now, ionic polarization. This is a very simple than electronic polarization or electronic polarizability. Now, ionic polarizability we are going to determine, and we are going to solve for it. So, ionic polarization occurs in ionic materials. Electronic polarization occurs in monoatomic gases, whereas ionic polarization occurs in ionic materials. It occurs when an electric field is applied to an ionic material, then cations and anions get displaced in opposite directions, giving rise to net dipole moment. So, in the previous video lecture, we have already seen that the displacement of cations and anions creates some electric field. Okay, whenever the electric field is applied, then the displacement of these two cations and anions occurs, and due to that we are going to have the polarization. Okay, so now the example of is polyatomic gases and NaCl we have taken as examples. So first you can easily remember the things as first one, electronic polarizability example is monoatomic gases, and here it is polyatomic gases. Now consider NaCl. We all know about NaCl very well. So Na plus and Cl minus. So Na is the positive charge and Cl minus is the negative charge. When this is the diagram without electric field. When the electric field is applied, they are separated with the distances, and the separation increased with x1 and x2. So ionic polarization occurs due to relative displacement between positive and negative crystals in ionic crystal. Okay, in ionic crystal, these ions will be relatively displaced from their original positions. Due to that displacement, we are going to have the ionic polarization. If a crystal or molecule consists of atoms more than one ion, the distribution of charges around the atom in a crystal or molecules leads to the positive or negative. Okay, as a result, when lattice vibrations or molecular vibrations induce relative displacements of atom, the center of positive and negative charges are also displaced. Okay, so due to the displacement, the center of positive and negative charges are displaced, and the displacement is also independent of temperature. Okay, so when an electric field is applied, the positive ions are displaced through a distance x1 and also the negative ions displaced through position x2. So the total displacement is given as x is equals to x1 plus x2. This is the total displacement. So the positive ions are displaced through x1 and the negative ions are displaced through x2. So the total is equals to x is equals to x1 plus x2, total displacement. Okay, so now what happens here? Lorentz force of acting on the ions is E into E and on the negative ions is minus E into E. Okay, where E is the charge of electron. When the ions displace from their respective directions from mean position, a restoring force is developed which tends to move back the ions to their original positions. So the restoring force is equals to K1x1. So K1x1 is the restoring force and K2x2 is the another restoring force. Okay, so the restoring force K1 is equals to, whereas K1 is equals to m omega naught square. Okay, where omega is the angular velocity, omega naught is the angular velocity, K2 is equals to small m into omega naught square, where small m is the mass of capital M is the mass of negative ion or small m is the mass of the positive ion. Okay, we have got small m into capital M. So when at equilibrium position, the Lorentz force and the restoring force are equal, and then E is equals to K1x1. Okay, so see, E is equals to K1x1, x1 is equals to E by K1, where K1 is equals to m omega naught square, we have already seen, and here E is equals to K2x2, x2 is equals to E by K2, E by small m into omega naught square. So x is equals to x1 plus x2, E by capital M into omega naught square plus E by small m into omega naught square. E by omega naught square into 1, taking in common 1 by m plus small 1 by m. So this is the x value, mean equilibrium position. Okay, now the induced dipole moment is equals to mu is equals to E into x. So E square, E into, we have substituted here E into E by omega naught square into 1 by capital M plus 1 by small m. So this is mu I. So mu I means ionic polarization, right? Ionic polarizability. So mu I is equals to alpha I into E. Same. So alpha I into E is equals to E squared by omega naught square into 1 by small m into capital M. So alpha I is equals to E squared by omega naught square 1 by small m into 1 by capital M. Thus the ionic polarization is inversely proportional to the square of natural frequency of ionic molecule. Okay, square of natural frequency of ionic molecule. Omega naught is the angular velocity, and also it is inverse, so that it is said that it is inversely proportional to the square of natural frequency of the ionic molecule. Okay, this is about ionic polarization. So in this ionic polarization, what we have learned, just we took an example of NaCl, and when the electric field is applied to the NaCl, the positive ions shifted to a distance x1 and negative ions are shifted to a distance x2. Then a restoring force will be created between them, and that restoring force is equals to K1x1, where K1 is equals to capital M into omega naught square. It depends upon the omega naught is the angular velocity, since they are moving as in the form of a spring. The restoring force will be there in order to bring the spring to its original position. Likewise, here whenever we are applying the electric field to the ionic ion NaCl, then what happens here? A spring action will be done between Na and Cl. Okay, due to that action, they have separated by distance x1 and x2 from their original from their equilibrium positions, and the total displacement is equals to x1 plus x2. So by solving the equations, what we have obtained? We have obtained alpha I is equals to induced dipole moment is equals to E square by omega naught square 1 by capital M plus 1 by small m. Okay, so where m is the mass of the positive ion and small m is mass of the small m is the, okay, Capital M is the mass of the positive ion and small m is the mass of negative ion. Okay, this is finally about the ionic polarization. Now coming to the orientation polarization. Here in the orientation polarization, space charge polarization, we do not have the particular mathematical equations. These will be occurring in a particular materials, and these will be occurring in particular molecules. So, orientation polarization is the polarization that occurs due to rotation and alignment of permanent molecular dipoles in the direction of applied field. Okay, so there will be rotation and the alignment of permanent molecular dipoles will be there in orientation polarization. Okay, in materials containing polar molecules such as H2O, the example are water and HCl. These are the examples. Remember the examples as well. Okay, each molecule already possesses a permanent dipole moment due to asymmetric charge distribution. In the absence of electric field, these dipoles are oriented randomly because of thermal agitation, resulting in Z net dipole moment as 0 at macroscopic level. This is shown in the first diagram. Before the application of electric field, then they are oriented in different directions. Whenever electric field is applied, these permanent dipole moments experience a torque that tends to rotate them towards the direction of the field. So, they are going to rotate in the direction of the field. Previously in this diagram, you could observe previously they are moving at random directions, where in this field they are moving in the direction of applied field. Okay, so the net dipole moment develops inside the dielectric materials, and therefore orientation polarization is highly temperature dependent. Higher temperature reduces the degree of alignment and therefore reduce the magnitude of the polarization. Okay. Now this is orientation polarization. This is simply H2O and HCl are the examples of orientation polarization, where in the orientation polarization there will be random moment of random dipoles will be created and moves in a random direction, and whenever the applied electric field is applied, then they move along the direction of the applied electric field. This is happened in H2O and HCl molecules. Okay, this is orientation polarization. Now coming to space charge polarization. Space charge polarization is also known as interfacial polarization. Yes, in the previous video lecture, we have already known about the space charge polarization. It occurs in very less materials, or very less molecules are going to have the space charge polarization. Almost the space charge polarization taken as 0. Okay, now, so the space charge polarization is also known as interfacial polarization. It is observed in multi-phase materials. The materials which defects are known as multi-phase materials. Where the defects are there, they are known as multi-phase materials, and the space charge polarization occurs there. The space charge polarization arises due to the accumulation of charge in lattice vacancies of the material. So, if the material is having any vacant spaces in between them, any void spaces, we have learned that void spaces in crystallography. Okay, so what are void spaces means? The empty spaces that are there within the atom are the void spaces. Here also, whenever there are empty spaces or vacancies in the lattice of the material, then the accumulation of the charges occurs in that material. Due to that, we are going to have the positive and negative charge centers will be developed and separated by small distance, which results in the dipole moment. This dipole moment gives rise to polarization known as space charge polarization or interfacial polarization. Okay, so see the diagram over here. Whenever there is no applied electric field, the positive and negative charges are randomly shifted like that. Then when the applied electric field is there, the positive and negative charges align in the direction of electric field. Okay, so the net dipole moments for these type of this is a very rare case where the defects are there in the materials, so that the space charge polarization will be occurring rarely. So what is alpha, final alpha, total alpha is the total polarizability, electronic plus alpha ionic plus alpha orientation. In some cases orientation polarization will be there, plus alpha space charge polarization will be there. This is the final polarization occurs from all the types of polarizations. Okay, so in this video lecture you have learnt about the types of polarization. In the next video lecture you are going to learn about ferroelectric and ferromagnetic materials, and also you are going to learn about the different applications of the magnetic dielectric materials. Okay, thank you.